back. We'll be continuing on the theme that we've established throughout these videos, and that's the notion that there's a parallel between translation and rotation. We're going to see that here with angular momentum. I kind of want to pause for a moment. As you've been studying this material, you might be wondering, what's up with this parallel? These concepts are all really similar, and it's amazing that they are. It's actually absolutely no accident, and that's part of what makes this really interesting. There's an underlying symmetry in the way that these equations manifest themselves, and if this was a more advanced course, I would be explaining exactly why this is. But for us, it suffices just to realize that there's a way that these equations are connected. To motivate this idea of the symmetry of these equations, I'm going to make a chart of them, and we're going to add angular momentum to this chart. So far here, we have three equations that we already know. The first equation that we know is the linear momentum equation, and that says that P vector is going to be equal to mv vector. While we're on this linear side, we might as well put in our equation for Newton's second law for translation. So that says that the sum of the forces is equal to the mass times acceleration. And from the torque video, we know that the sum of the torque vector is equal to I times alpha vector. Okay, so we're already seeing some patterns emerging here. So we could kind of guess at what our angular momentum equation is going to be. The angular momentum equation is going to be L is equal to I times omega. Now here's the really interesting part. Now that we have this grid, we can talk about the way that each one of these equations is related to each other. So let's first start on the left. We see that for our momentum and our Newton's second law, we both have masses here. But there is something that's different, and that's the velocity and the acceleration. But our velocity and acceleration are actually themselves related to each other. So these are related to each other because the acceleration, A, or the average acceleration, is going to be equal to the change in velocity divided by the change in time. Okay? We're going to see something very similar on the right side of the equation. So again, we can see that we have this common term here. This is going to be our moment of inertia. And we can relate the angular velocity to the angular acceleration by saying that the angular acceleration alpha, as an average, is going to be equal to the change in omega divided by the change in time. Okay, so that's kind of interesting. But we have another relationship that we can draw here, and that's the relationship between the force and the torque. So in our torque video, we talked about what gives something a torque, right? So we said if we had some lever arm, we have some pivot point, we apply a force, and that torque is going to be equal to the length or the distance from the point of rotation to where the force is applied. And we want the force that's going to be perpendicular. So what we can say is that torque is related to force by saying the torque is going to be equal to R times F perpendicular. Right? This is just recapping some of the things that we had in our previous video. Well, at this point, you know, it feels a little bit like beating a dead horse, but it might come as no surprise to you that there's a relationship between momentum and angular momentum as well. And that relationship takes a form that's very similar to the equation that we had for torque down here. Now, if you want to pause the video and guess at it, you're more than welcome to, but I'll just write it here and say that the angular momentum L is going to be equal to R times P perpendicular. This is really interesting, isn't it? Because we know how to deal with these equations already when we have a distance and a perpendicular vector that we're trying to say something about. when it comes to the way that we talked about torque. So really, the way that we're going to talk about angular momentum really mimics the same behavior as this equation for torque. And it's beautiful in its own way, and it's very interesting that the equations end up manifesting themselves like this. Okay. Now there's one other thing that I can say for these equations to finish my chart here, and that's to consider the conservation equation that we had before. So on the second test, we talked about momentum conservation, in particular the conservation of linear momentum. And so what that said is if I have two states, an initial state and a final state, the sum of the momentum initial, and this is a vector, is going to be equal to the sum of the momentum in the final state, or after. Well, wouldn't you know it, we have another equation like this on the right side, and that says that the sum of the angular momentum initial is going to be equal to the sum of the angular momentum final. Okay. So I don't really have too much to say about any more of this because, like I said, there's very strong parallels between these two equations, and we've talked at length at how to use this torque equation. And so all of those rules that we applied before when we were talking about a force that acted on an object, what's the distance to the between that force and the point of rotation, and trying to make that the perpendicular component apply for doing angular momentum. And now we're just doing this with a momentum instead of a force when we're talking about perpendicular components. Okay, so that's going to be it for this video.